That's right.
You ever any still came to school?
I mean, I didn't think I was in that bad a shape, but I went to the doctor later, and he said, "Yeah, you probably had a minor concussion."
Oh, try don't stop.
Yeah. We're going to talk about derivatives of a transform. Why am I having such... What's going on with my thing here?
Oh, we did transforms of derivatives.
Yeah, we did transforms of derivatives before.
Look at the transform of the derivative, not the derivative transform.
Close. Close, but not quite, unfortunately. So today we want to find a transform. Why is this running so slowly? Of some function multiplied by t to some power. So to do this, we're going to assume that we know the transform of f of t. So we're going to say big F of s equals the transform of f of t. So what we're going to do is look at the derivative of this transform. So the derivative with respect to s of f of s is going to be the derivative, by our definition, from 0 to infinity of e to the minus st f of t dt. And we're going to assume, under specific conditions on our function, we can interchange the order of differentiation and integration. So we're assuming that our function allows us to do this. It's not necessarily the case, but we're assuming that it works for the function we're talking about. So that's going to be e to the minus st times f of t dt. Well, now we can take the derivative here. The derivative of e to the minus st with respect to s that's equal to negative integral from 0 to infinity e to the minus st, and then the derivative of st is t times f of t dt, which we can rewrite as negative Laplace transform of t f of t. And so equating our two things, we get that the Laplace transform, so we started here, the Laplace transform of t f of t equals negative dds of the Laplace transform of f of t. I'll rewrite this in our other notation. dds of the Laplace transform of f of t. So Laplace transform of a function multiplied by t is the negative derivative with respect to s of the Laplace transform of the function. And then for t squared f of t, t squared f of t. We're going to get the Laplace transform hang on. Oh, I know what's wrong now. I was using the old board. The pen in this one is not doing great. Actually, it's an old pen. That's a new board, but an old pen. This is the old board, the new pen.
Oh, mix and match.
Well, the battery is going dead in this board. Like I'm having to recharge it pretty frequently. But I don't want to start using the new one until I have to, so the new one will last until I retire.
How many of those things have you gone through?
4. Mr. Leader would go through several a year. He was not easy on his equipment. I'll put it that way.
Did he like rage throw them around? It didn't work.
So the Laplace transform of t squared f of t is going to be the Laplace transform of, I'm just going to separate these, t times tf of t, which is negative derivative with respect to s of the Laplace transform of t f of t. We're treating this as our function multiplied by t, which is equal to minus the derivative with respect to s of minus derivative with respect to s of L of f of t, which is d squared ds squared Laplace transform of f of t. And we could go on for our third derivative, on our fourth derivative, etc. So we generalize this to get our theorem about the Laplace derivatives of Laplace transforms. And all this comes from applying this operation to the definition of our Laplace transform. So we're good with the steps here. See, we understand. So our theorem. So we're going to say f is piecewise continuous. On 0 to infinity and of exponential order. We're making sure that it has a Laplace transform and that the Laplace transform of our function is big F of s. And I'm going to say then for n equals 1, 2, 3, dot, 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 and s greater than c. C is that constant for our function to have exponential order. The Laplace transform of t to the n f of t equals negative 1 to the n times the nth derivative of the Laplace transform of f. So the derivative of Laplace transforms has to do with have to do with functions multiplied by some power of t. So this gives us a way to find Laplace transforms of an additional group of functions. And really that's what all of everything we've talked about since we talked about the definition is, well, how can we use what we know to expand the types of function we can take the Laplace transform of. So I want to do a couple of examples. We'll solve a differential equation, and then we will look at certain types of differential equations where we can apply the Laplace transform and transform this certain type of differential equation into a linear differential equation that then we can solve using techniques that we've learned previously, which is kind of our general technique for solving differential equations. We do some kind of transformation to turn the differential equation into another kind of equation. All right, so questions, are we clear? Are we good on our theorem? It's not particularly complicated theorem here. The difficulty, not the difficulty, but the challenge, the issue, the crux of these things often for finding the Laplace transform, if we're not looking them up in a table, is doing these derivatives. So this is going to be -1 squared times the second derivative with respect to s of the Laplace transform of cosine of t, which is equal to the second derivative, and I think we probably can visualize why finding these derivatives is a thing. S over s squared plus 1. Almost all of our Laplace transforms are some kind of fraction, so we have to use the quotient rule. And here we have two derivatives that we're taking to do this. So after our first derivative, so we take one derivative, and we get, using the quotient rule, we get negative s squared plus 1 over s squared plus 1 squared. So now we have to take the derivative of this. So another nice quotient rule. I'll leave out all the intermediate steps, but I'll show you. There's my work here. You can see the
Is there any online thing that can help us with this?
I don't think there's anything online that will take derivatives for it. Nothing pops into my head. 2s, s squared minus 3 over s squared plus 1 to the third. There are a few steps in between there, in between this and this. A few steps in between this and this. But we're just taking derivatives. Now, to find the inverse transform of something like this is challenging if we were doing it without looking in a table, because somehow you have to recognize that this is some kind of derivative of some other function of s. So usually, for things like this would definitely be something you would look up in the table for the inverse transform. Let's look at another one. We'll do it. This one has a little combo of techniques here. We want to find the Laplace transform of t e to the minus 3t cosine t. So before today, this was an example of a problem that definition would be kind of a mess to do because we have so many integration by parts going on here. But now we have t times some other function. So this is going to equal minus the derivative with respect to s of the Laplace transform of e to the minus 3t cosine t. Well, now for our Laplace transform, we have the Laplace transform of a function multiplied by an exponential function. So what is that doing? That's a shift. So we're going to get a shift in our, this is our s shifting. So this is equal to minus the derivative with respect to s of, this gives us a shift, so we get, and we're doing the derivative, the Laplace transform cosine, s plus 3 over s plus 3 squared plus 9. Because the Laplace transform of cosine of t is s over s squared plus, this should be a 3t. That's where the 9 comes from. Laplace transform of cosine of 3t would be s over s squared plus 9. So now we're taking the derivative of this. Again, a quotient, so we have to use the quotient rule. This one's not a terrible one to do. But we end up with s plus 3 squared minus 9 over s plus 3 squared plus 9 squared. And as we learn more techniques, this is kind of what illustrates what can happen as we end up to do a Laplace transform, to do an inverse Laplace transform. We're recognizing multiple things combined that we learned. T shifting, S shifting, derivatives. We'll see integrals next time. And again, to find the inverse transform of this, somehow you'd have to do it without a table, you'd have to recognize somehow that this is a derivative of some function. And we see the shift because of the s plus 3 quantity. Generally, this is something you'd look up in a table.
Yeah, I need this whole saving.
That's in our appendix C. The very back, in the very back of the book. Giant table of Laplace transforms. Here, I'll be right back. I'm going to grab a book.
Josh, come to class. Mr. Beamer ran out because you don't come to class.
Well, I use that table for a lot of stuff.
Oh,
You
that's
have
nice.
that table in the back now.
Well, I don't have this table.
So this was CRC, Standard Mathematical Tables and Formula. The one I had in college was a little smaller and it was green, and I carried it with me everywhere I went. But let me look here.
Did you have the calculator down thing there?
No.
No, I'm afraid I'll take it. Tell me what page it is. Well, I just assume
I just have to find the right place. Laplace transform, 479. Yeah, I had the integral table bookmarked in mine because we had to. Where's our tables of Laplace transforms? Tables of transforms, 492.
Seems like easy doing that instead of just searching.
Yeah, a lot of times it was search and search and search and not find it. And that was frustrating. So yeah, a lot of transforms there.
How do they like sort?
Just the form of the function. Yeah. So that's big tables of Laplace transforms. That's what we used. That was our. This replaced. What we used in place of Wolfram Alpha or ChatGPT now, I guess. But this was correct.
It's not really answered. It can tell you those steps.
Yeah, ChatGPT. The problem with ChatGPT is it's a language
Yeah.
AI, so it sees math symbols as words, and it puts the words together in really nice ways, but not necessarily mathematical ways.
I think it has partial fractions. It's nice.
I got a headhunting offer recently for training AI how to do math problems.
That's sweet.
I said, I wonder if they would still pay me if I did everything incorrectly.
The AI would complain way less than your students.
What's that?
The AI would complain way less than your students.
That's what
Was it ChatGPT or what? Like.
I don't know what AI it was.
Yeah.
But yeah, it was to train AI to solve math problems. All right, so this is our differential equation. Do we recognize this? This is undamped, driven, simple harmonic motion. So a mass spring system, undamped, driven by this function. So we're going to use the Laplace transform here. We could solve it. What would be our choice otherwise? Undetermined coefficients or variation of parameters. Yeah, if we did undetermined coefficients, we'd have what y sub p is a sine t plus b cosine t. So that wouldn't be terrible.
Something like that. It's better one.
So we get this. So s squared y of s, this should be a capital Y, y of s, minus s y of 0, minus y prime of 0, plus y of s equals 1 over s squared plus 1. And I'm going to substitute. This is 1 and this is negative 1. So we get and combine the y of s terms. So we get s squared plus 1 y of s. And anytime you do this, I mentioned this last time, this coefficient on your y of s should be kind of like our characteristic equation for this, or a polynomial, characteristic polynomial. So s squared plus 1. And we have minus s here for this, plus 1 for this minus negative 1, equals 1 over s squared plus 1. So take these over to the right-hand side, divide by s squared plus 1. So we get y of s equals 1 over s squared plus 1 squared plus s over s squared plus 1 minus 1 over s squared plus 1. And then we say y of s equals, I'm going to write the inverse transform of s squared plus 1 squared. Sorry, sorry, 1 over s squared plus 1 squared, plus the inverse transform of s over s squared plus 1. Do we remember what that one is? That's a cosine. 1 minus 1 over s squared plus 1, sine t. This one I would look up. When I see that squared in the denominator, so I'm going to go to my table in the back here, of the back of the book, and I see number 25 says, I'll write it out, the Laplace transform of sine kt minus kt cosine kt equals 2k squared over s squared plus k squared squared. So here k is going to be 1. So we're missing that factor of 1/2. So we get that this equals y of t equals 1/2, because I don't have the 2 here, so I'm doing 1/2 of that. 1/2 of sine of t minus t cosine t plus cosine t minus sine t. And this t cosine t, that's how we get this s squared plus 1. In the denominator, we're taking a derivative. This tells us we're taking a derivative. And we've solved that differential equation. And this t cosine t, if we had used undetermined coefficients, cosine t shows up in our complementary solution, so we have to add that factor of t. So that's where that t comes from. If we're thinking about solving it the way we would have in the past, or the way we could in the past, or our other technique we might choose to use. Laplace transform is better, or the other techniques are better? For initial value problems, Laplace transforms are just really
It
nice.
depends on how hard the inverse transform is.
How hard the inverse transform.
So, yeah.
We just need like a huge table.
A huge table. The hard part with a big table is it's like, oh, does it match this one? Is it like this one, or is it like this one?
Could we use
Yeah.
that, like, could we use that, like, where it's a giant table, like that one in the back corner? Like, could we write the table on that? So, like, what if we need it mid-test? Mid-test, we would all be just looking at this back corner. Yeah. It's empty right now.
So for the quiz, I'm just going to give you the basic little table.
Okay.
I know for the final, they provide a specific table of Laplace transforms.
The ones that you need.
Right. It's not a giant table, but it's a bigger table than our basic one. So that's for our chapter 16 test. I would probably have some kind of table, more robust table than the basic one, but not. We don't need everything that's in the back of the book, because there's some stuff here that we're not really going to look at. There's error functions and various other things in there.
When we get to the final, how do we know whether we use Laplace or whether we use something else, or just making?
So there will be some problems that say use a Laplace transform to do this. But if it doesn't say, then you can choose. All right, I want to look at one more thing today. So sometimes we can use this theorem to solve differential equations with variable coefficients in the form a t to the m. So our other techniques generally didn't allow us to solve differential equations with variable coefficients. All of the differential equations we solved previously had constant coefficients. Variation of parameters can be used in theory to solve differential equations with variable coefficients, but we really didn't talk about it. There's one specific type of differential equation with variable coefficients called the Cauchy-Euler equations, where the exponent on the t matches the order of the derivative of the term. So there's that specific kind. But here we can apply this to differential equations with any coefficients a, t to the m. So what we do is we transform the equation into a lower order differential equation in S. So our differential equation in S then would be a linear differential equation that we can solve We solve that differential equation using techniques that we've learned before, separable, first order linear with an integrating factor, for example. We solve this equation and then apply the inverse transform. And just as a heads up, there are a couple of the homework problems for this section where you do need to solve first order linear differential equation by using an integrating factor. So when that comes up, you'll be prepared. So we want to solve t y double prime minus 4t y prime minus 4y equals 0. And we have y of 0 equals 0 and y prime of 0 equals 5. So with the techniques that we've learned previously, we would not be able to apply to this differential equation. But now that we know the derivative of a transform, we can solve this. So we're going to take the Laplace transform of each term, t y double prime minus 4 Laplace transform of t y prime minus 4 Laplace transform of y, and that's going to equal 0. It's nice that this equals 0. Well, Laplace transform of t y double prime is minus the derivative with respect to s of the Laplace transform of y double prime. This is plus 4, and it's plus because we're doing the negative derivative of Laplace transform of y prime minus 4 Laplace transform of y is just y of s, and that equals 0. So really what we've done here is add another layer on top of the type of differential equations that we've already solved. Because we've done differential equations with the transform of y double prime and transform of y prime and y there. So we end up taking some derivatives with respect to s once we do the transforms. So this is minus the derivative with respect to s of s squared y of s minus s y of 0 minus y prime of 0 plus 4 derivative with respect to s of s y of s minus y of 0 I know some y of 0, 0. I'm just writing things out explicitly. Minus 4 y of s equals 0. So I need to take some derivatives here. I need to be careful here because both of these are derivatives, or sorry, are functions of s. So we're using the chain rule here. Y of 0 is 0, so I don't have to worry about that. And y prime is 5. We're taking the derivative of a constant there, so that ends up not impacting our derivative. So we end up with minus s squared y prime of s minus 2s y of s when I use the chain rule here. Plus 4, we get s y prime of s plus 4 y of s. I need to move this down or move this over. So this comes from taking the derivative of s y of s. We're using the chain rule and we're multiplying by 4. Minus 4y of s equals 0. And this should be 4y of s here. Those cancel, yes. I'm going to gather the terms that involve a y prime, and I'm going to gather the terms that involve a y of s, which is just this one now, because these cancel. So we get 4s minus s squared times y prime of s minus 2s y of s equals 0. So now we have a first order differential equation in S. So we transformed a second order differential equation in T to a first order differential equation in S. I'm going to put it in standard form. I want my y prime by itself. Y prime of S minus 2s over 4s minus s squared y of s equals 0. I can cancel one of these s's here. So we get y prime of s minus 2 over 4 minus s y of s equals 0. What kind of equation is this? What technique would we use here? Y of s equals minus, wait, what did I do here? What did, I'm going to write this, this s minus 4 minus s to s minus 4 and change this to a plus because our Laplace, inverse Laplace transforms have an don't have a 4 minus s. So I'm going to do this as s minus 4, and then this turns to a plus. So we end up with minus 2 over s minus 4 y of s. This is dy ds. This is just y. This is separable. Now you could use the integrating factor here. From here, it will work. The integrating factor, using the integrating factor will work on separable differential equations. So we're going to separate this. The way we'd write it when we do the separable equations, dy ds equals minus 2 over s minus 4 y. So we get dy over y equals minus 2 ds over s minus 4. So the natural log of y equals minus 2 natural log s minus 4 plus our constant of integration, which I'm going to write as natural log of s minus 4 to the negative 2 plus our constant of integration. We exponentiate both sides, and we get, and we rearrange. We get y equals e to the c, which is just, I'm going to call c1, over s minus 4 squared when we exponentiate this. And this is y of s. So y of t is c1 times the inverse transform of 1 over s minus 4 squared. What was that? This is a shift. So I can rewrite this as c1 inverse transform using the notation that the text uses, 1 over s squared. We're evaluating that s to s minus 4. So we get y of t equals, well, the shift gives us an exponential function. This inverse transform of s squared is t, so we get e to the 4t. Isn't that nice? So we have transform of the derivative, we have the derivative of the transform, we have separable differential equation, we have a shift. All of that stuff gets mixed into a nice little problem there. Guess it's not until after break. There's one example that involves a step function, and then it involves an infinite geometric sequence, and then a nice inverse transform. Just all this stuff gets mixed up into a nice what do I want to call it? Jack Black would call it a goulash. We're making a nice sauce of math stuff, mathematical sauce.
How much favorite example from this semester?
Oh, the one that I just worked out for the lesson, that one's a pretty good one. That's a pretty tame homework assignment there. Oh, I'm going to give you a note for number 21. For number 21, you need to look at the limit as s approaches infinity of the thing that you come up with to get your final answer. I don't know, some of those the systems with